So today, the first part is going to be finding a polynomial function based on its roots. So I'm going to start off with, this is not something that's new for you guys. It's a backwards application of something you already learned how to do. Honestly, probably in Algebra 1. Hopefully in Algebra 1. Okay. So back in the Stone Age, when you first learned this, is my pen working? Where is my pen? Hello, pen. There it is. All right. Back in the Stone Age, when you started working on quadratics, you would get an answer that looked like, I don't know, x minus 2, x, that's not an x at all, geez. X plus 1, right? Like you factored it, you get the factored thing, and then you'd say this, you'd set them both equal to 0, and you'd say, hey, the answers are x equals 2 and x equals negative 1, and then you were done. We're going to do this, but backwards. So I'm going to give you the x's, the x equals, and then you're going to tell me what the equation was. It's a lot simpler than it sounds. If you're anything like me and you have like visual learning problems, I have a problem with visual learning because of my dyslexia. Color coding did help me when I first learned this. Now I don't need to do it, but at first I really did because my brain hates me. I think that's the takeaway of my dyslexia is my brain hates me. All right. So what I'm going to do here is exactly this. I've got 3 zeros, 0, 2, and negative 3. The question that I would expect here is, how do I write this as a factor? If you think about it, when we were doing these up here, we said x minus 2 equals 0 to get the positive 2. We said x plus 1 equals 0 to get the negative 1. So what can we set x equal to get a 0 is just x, because it'll be x equals 0 when we set the equation up. So I'm going to write this as x for my 0. My 2 will be x minus 2. Remember, it's the opposite. The negative 3 will be x plus 3. What I tend to do with these is pick 2 factors to multiply to get a trinomial and then distribute into that trinomial. Your mileage may vary. If you have your own method you want to do, I'm not going to complain about it. So I'm essentially just going to take this x and put it like this. I'm going to say x times x squared, x times 3 plus 3x. Negative 2 times x will be minus 2x. And negative 2 times 3 will be minus 6. And then I'll clean up the inside. I'll collect my like terms. X times a quantity x squared plus x minus 6. Then I can distribute this x across. So we get x cubed plus x squared minus 6x. And this is the equation that has the answers of 0, 2, and negative 3. If you wanted to distribute this x and then distribute that, that's totally fine. Whatever you want to do. This is just the way that my Algebra 1 teacher, Mr. Jackson, taught me how to do it by making us do it 1,000 times over the course of 3 weeks. I love you, Mr. Jackson, but I'm sorry I hated doing that. All right, so let's do a couple of these bad boys. I'm going to show you my kind of tips and tricks and number sense. So in these, the second one we're going to do here, you can, what I would call it is brute force. You can just sit there and multiply it out. But there's a shortcut we can take to do less work if you have good number sense, and I'm going to explain that in a second. So this guy, all right, n equals 3, so I'm going to have 3 factors, right? Should be a cubic function. My zeros are, well, 0, so x. I've got an x minus 5 and an x plus 7. This works the same way. So I'm going to multiply the binomials and then put the x in there with distribution. So the fancy math teacher, x times x squared, x times 7, 7x, negative 5 times x, negative 5x, negative 5 times 7, negative 35. Then distribute my x across. We'll get x cubed, so it's degree 3. That works. Plus, let's see, 7 minus 5 is 2. So it's 2x squared. And then minus 35x. And that's it. All right. Now, the next one. This one can be long, but this particular problem is actually not long. So I'm going to write it out, and then I'm going to point out my number sense here. So I have positive and negative 1 and positive and negative 5. So x plus 1, x minus 1, x plus 5, x minus 5. Now I could multiply this out, but I see a pattern here. In this particular binomial, where'd it go? Where's my mouse? There it is. This particular binomial is a special name. It is a difference of squares, right? And we know difference of squares, the middle term just goes away. So we square the first term, and then we square the last term. So I'm going to shortcut this to x squared minus 1. So x and then negative 1, right? And then the other one is going to be x squared and minus 25. 5 times 5. Now it's a lot less to multiply. Essentially, we did these two and these two together. But I'm using number sense to do honestly the least amount of work that I have to do. So this is easier to multiply. X squared times x squared, x to the fourth. X squared times negative 25 will be minus 25x. Was x squared. Negative 1 times x squared will be negative x squared. And then negative 1 times negative 25 will be positive 25. Combine my middle terms, x to the fourth minus 26x squared plus 25. So these aren't too bad. They can get icky. And honestly, if they get icky, I just multiply 2, ignore the other 2 for a second, multiply 2, get that answer, multiply times the next one, take that answer, multiply times the next one. Just make a pattern, get yourself in the groove of it. If you can use a sheet in bunny rabbit ears like this, go for it. So what happens if we have an equation that doesn't have all real solutions? Because we did imaginary numbers, sometimes you end up with an imaginary solution. That's okay. And we talked about the conjugate root theorem a while ago, and this is an interesting application of it. So in case you forgot, it says if a plus bi, where b is not 0, is 0 of the polynomial function with real coefficients, the conjugate a minus bi is also a 0. Blah, 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 blah. What that means is if I have, let's say, a 0 of 3 and negative and 4i, that negative 4i is also a root. Why does it matter? Without the conjugate, we're not going to be able to go backwards. Also, it's true that it would be the other root. So here is kind of our workflow for this. If we get something with a complex root, or an imaginary root in this case, it's not complex, what we're going to do is we're going to write down what our zeros are first. So my zeros are 3, 4i, and then 4i's conjugate, negative 4i. And we're going to play this the same way we played the other one. We're just going to multiply these 3 in a row. So my factors are x minus 3, the opposite, right? We've got, don't forget the x, Mr. Clark. X minus 4i and x plus 4i. So what I'm going to do for a second is take this x minus 3. I'm going to, like, in my mind or on my paper, if I had, movable paper, I'm going to take it and put it off to the side for a second. I'm going to ignore it. And I'm going to work on getting this I situation sorted out. Now, when we look at this, where'd my mouse go? There it is. We've got x minus and x plus. It's a difference of 2 squares. So that middle term we know is going to disappear. The middle term is what's going to be our I term. Let's go ahead and multiply this out, and you can see what I'm talking about, in case you don't remember from when we did our little unit on complex numbers. X and x squared, x and then plus 4, plus 4i would be x 4i. And we'll do negative 4i times x, so minus x 4i, or 4xi would probably be a better way to write it, but they're going away, so who cares? We've got a negative 4i plus a positive 4i, so we get a negative 16i squared. These middle terms, they go away. And again, it should have been 4xi if I was being proper, but whatever. This I squared, remember I squared is a negative 1. So it just effectively changes the sign of the last number. So I get my x squared, and now I get a plus 16. So when we were doing these, basically, you square your first term, and you square your second term and take the I off. That's kind of like the gist of what the math does to the problem. So if ever you're like, did I do it right? That's kind of your sanity check. So that means that we've got x minus 3, what we put aside, and all this complex stuff simplified down to x squared plus 16, which is way easier to handle when we're doing our work. So I'm going to write down before I forget. We said x minus 3, x squared plus 16. And now I multiply these two binomials together to get the equation that would have got me all those answers. So x times x squared gives us an x cubited. X times 16, so we get a 16x. Negative 3 times, oh, sorry. Wait, no, that was right. Yeah, 16x. Negative 3 times x squared will be negative 3x squared. And then negative 3 times 16, negative 48. I promise I know my 16s from programming. All right, do I have any like terms I can collect? Doesn't look like it. So I'm going to put them in descending order, make it look fancy. X cubed minus 3x squared plus 16x minus 48 is our equation that would get us the zeros of 3 and then 4i. Okay, this should be interesting. What's our next one here? I thought I did more than one with complex roots. Well, there you go. Let's take a look at this. I'm anticipating this is going to be kind of a mess. And the reason is we're going to have a fourth degree equation when we're done. So that means we're going to have 4 of those delightful binomials. Guess we just get started and power through it. X, it's positive, so minus 3. X, it's negative, so plus 4. We've got a double root of x equals 2. You could write that as x minus 2 squared if you wanted to. I'm going to write it as x minus 2, x minus 2. The only reason I'm writing it like that is because in my experience, students tend to get confused when I do like an x minus 2 squared. They don't understand that it's really those two. A lot of people want to square the x and square the negative 2, and I don't know. I just work here. So what I am thinking is that we multiply those two together, and we multiply those two together, and then whatever those solutions are, we can multiply those two together. Always go into it with a plan. All right, so this guy will be, let's see, x squared. We've got 4 minus 3, so that'll be plus x. And then negative 3 times 4 would be minus 12. Hope you don't mind, I'm doing a little bit of a shortcut on my multiplying there. X times x, x squared. Negative 2 plus negative 2 will be negative 4x. And then negative 2 times negative 2 will be plus 4. I like taking shortcuts where I can. Okay, this is going to be fun. Let's see if I can write this in a straight line and not go crazy. All right, here we go. X squared times x squared. X to the 4th. If I miss anything, you guys let me know because this is a lot. x squared times negative 4x should be negative 4x cubed. X squared times 4 should be plus 4x squared. X times x squared will be plus x cubed. X times negative 4x will be negative 4x squared. X times 4 will be plus 4x. Negative 12 times x squared will be negative 12x squared. Negative 12 times negative 4x will be plus 48x, yes. And then negative 12 times positive 4 will be minus 48. Did I miss anything? We did this one, we did this one, we did this one. Okay. What I'm going to do, and you don't have to do this, but I'm going to, for my own brain, I'm going to look at the like terms. I've only got 1/4. Here's the cubes. Here's another cubed. Here's a square. Here's another square. Here's another square. Here's an x. Here's an x. Okay. Sorry, that was just for my own sanity. So I got an x to the 4th. I got a minus 4x cubed and a plus 4x cubed. It'll be negative 3x cubed. Plus 4 minus 4, they're gone, so minus 12x squared. I've got a 4 and a 48, so 52. And then a minus 48. And I hope I got all those numbers right, because that's a lot. Aren't you glad we didn't have to solve that disaster? Holy cow, that would have taken a hot minute. So they're not hard. When you get to 4th and 5th root, I don't think I gave you any 5th root. 4th root can take up some time and space. And I'm not going to judge you if it does. You know, I'm not that kind of guy. Okay, so quickly review this piece. To find a polynomial function, write zeros down, multiply it out, and go backwards, just like we do with quadratics when we're working on quadratics. If you end up with an imaginary number or a complex number, remember, use the complex conjugate. And my personal tip is go in with a plan before you start multiplying so you don't confuse yourself. I color code, but that's, me personally. All right. Here comes the one that is a little, this looks really hard and is not, okay? We're going to talk about finding the roots of polynomial functions. So let's say that I give you an icky polynomial, and I say find the roots. And you have to do it without a calculator. I guess, or with a calculator, honestly. We would use a couple different theorems. The first is the rational root theorem, which looks like a disaster, right? If polynomial function f of x equals a sub n x to the n plus a to the sub n minus 1 x to the n minus 1, it looks complicated. What we are really looking at, which would be easier if you could actually see all this, is just a bad scan, is this idea of p over q, and this idea that a is not equal to 0, which if it was equal to 0, we'd have other problems. So this will determine the possible rational roots. This isn't going to deal with imaginaries. Mr. Clark, how am I supposed to interpret that mountain of words that I think are in English into something I can do in a math class? The English translation of this is you're going to take the last number, this last a value. In this case, in this equation, it's a -3, right? And we're going to put it as our p. So I'm going to write p and q like this. Our first coefficient, aka whatever is in front of this, in this case, it's going to be 2. That's our p over q. Okay. Now we're going to do something with this. What I'm going to do is I'm going to write down the factors of both numbers. So the factors of 3 are going to be 1 and 3, right? And the factors of 2 are going to be 1 and 2. I can use positive or negative. So my answers could be positive 1 divided by positive 1, negative 1 divided by positive 1, negative 1 divided by negative. Like this goes on and on, right? We could have a fraction. It could be 3 over 2. It could be negative 3 over 2. These are all of the possible solutions. That does help us, but if we don't handle this right, that means if we want to solve it, we have a ton of work to do. Imagine if it was 8 over 1, all the factors of 8, doubled, because positive and negative. Like that, it can be not fun. But I promise, if you know what you're doing, it's not too bad. So the first thing we're going to do is just practice figuring out what the possible roots are. So let's take a look at this other one. You'll see how easy it is. P over Q, last number over first number. Okay? The factors of 6 are 1, 2, 3, and 6. The factors of 1 are 1. So I have 8 possible answers. 1, 2, 3, and 6, negative 1, negative 2, negative 3, negative 6. My preference is to not check 8 different answers, but it is what it is. So this can yield a large number of possible roots. It is not giving you the answers, it's giving you possible answers. To help eliminate some possibilities, we can use Descartes' Rule of Signs. This rule doesn't tell you what the roots are, but it does tell you the maximum number of positive and negative real roots. All right, so basically step 1 is here is my pool of possibilities. Step 2, I'm going to use this thing that Descartes came up with to figure out how many I'm looking for out of that list. So I don't know how Descartes came up with this. He was a pretty stinking smart guy. Little known fact, he and Sir Isaac Newton actually came up with the ideas, the fundamentals of calculus at the same time, and there was a race to see who got published first. And Newton, I hate to speak ill of the dead, was kind of a jerk and ended up winning the race to get published first, even though Descartes was honestly kind of doing the same thing. So this dude was super smart, also a philosopher. Okay. This is something that sounds complicated and is not. The idea here is basically counting. So if you have some polynomial function with real coefficients, so no imaginaries, and a non-zero constant, that means a number at the end, arranged in descending powers, so standard form like we usually do, then this idea applies. The number of positive roots is the number of sign changes of the terms of f of x, or is less than that by an even integer. So let's say that our equation has 2 sign changes, right? An even integer would be 2. So it could be 2 roots, or it could be 0 roots. 2 minus 2, 0. It can't go into the negatives because it doesn't make sense to have negative answers. You've made a black hole at that point. If you want to know the number of negative roots, we're going to do the same thing, the number of sign changes. Sign changes, it's counting. Except we're going to evaluate for f of negative x. And it works same thing by the even integer. So if you had maybe 4 negatives, it could be 4, it could be 2, it could be 0. Mr. Clark, that's very nice. What? Okay. That was the same reaction I had when I learned this, so I'm trying to like put myself in y'all's shoes. Oh, what? Let's do one. All right, what we're going to do is we're going to look at this bad boy. We're going to determine the number of positive and negative roots. We're not solving it. We're just saying how many are in there. So I'm going to count. This is a positive. So positive and negative, that's one sign change. So that's 1, 2. So I have 2 sign changes. So I either have 2 roots or 0 positive roots, right? Let's see how many negative roots there are. What I'm going to do is take my expression and just replace x with negative x and see what happens. Okay, so if it's an odd root, sign changes. Even root, nothing changes. So I get negative x cubed. This doesn't change. It was squared. Odd, so it does change. And it's a constant, so we don't care. This is negative, so negative, negative. One sign change. I definitely have one negative real root. I can have less by an even number, but 1 minus 2 gives me -1, and that's nonsense. So I definitely have one negative root, and I either have 2 or 0 positive roots. That's how you do this. It's just counting. Let's do another one here. All right, so let's see. Oh, sorry. There are either 2 or 0, and there are 1 negative. So let's do positive first. Positive's easy. Positive, positive, positive. I got one positive root. I can't have -1 roots, so there's one positive root. To check for negatives, we're just going to evaluate for negative x. 2 negative x minus 3. This ends up being -2x cubed plus 7x squared minus 2x minus 3. So I've got 1, 2 sign changes. So my possibilities, well, I've definitely got one positive root. I either have 2 or 0 negative roots. That's the gist of this. So why do I care about this? If I was back up here with this thing where I knew the number of, or I knew all of the possible roots, once I have one positive, I know there's nothing else positive I've got to check. And then I can start checking the negatives. And I know if I don't get one, I'm done. Because I've got to have 2 negatives or 0 negatives. So this stops me from checking every single possibility in this rational root theorem. All right. I'm going to put this stuff together and do this problem 2 different ways. So way number 1 is I understand the rational root theorem and I do not like factoring. Way number 2 is I understand the rational root theorem and I do like factoring. So it's either I like factoring or I don't. Let's do the factoring method first. So I've got this guy here. Rational root theorem says 6 over 1, so my possibilities are going to be 1, 2, 3, and 6, just like before. What I'm going to do is go through and start checking possible rational roots. So I'm going to check 1. I'm going to check -1. I'm going to check 2. I'm going to check -2. I'm going to check 3. I'm going to check negative until I get one that does work. There is a long way to do this and there is a short way to do this. So the long way to do this is to solve that equation every time for each one of these. That takes up a lot of time and a lot of space. What we did before the break was synthetic division. And one of the cool things that synthetic division does is it will let you evaluate a polynomial for a given value very quickly, which is what I'm going to do because I don't enjoy doing it work I don't have to. So my equation, let me set it up for synthetic division. We had a 1, a -2, a -5, and a 6. My box. I'm going to start with 1. I'm sorry, I can't draw a straight line. Let me scoot this up a little bit. Should have gone to art school, Mr. Clark. That's pretty close. And I'm just going to do synthetic division. What this is going to do is evaluate my equation for 1. Let's see what happens. 1 times 1 is 1. Negative 2 plus 1 is going to be negative 1. 1 times negative 1 is negative 1. Negative 5 plus negative 1 is negative 6. Negative 1 times negative 6 is negative 6. 6 plus negative 6 is 0. When you get a 0 here, you know it is a factor. So we know that x minus 1 is a factor. Why is it a minus 1? This is the opposite of what your factor is, right? Okay, who cares? I know this factor. This thing here is also a factor. So if I bring this back into like algebra, this says x squared minus x minus 6. And I know I can evenly divide it by x minus 1. Could I keep putting these numbers into this? Yes, but why? We did factoring for what felt like forever. We can factor this in our head. I hope you can anyway. So this guy factors to x plus 2x minus 3 and x minus 1. So here's my solutions. My solution is x equals, let's see, negative 2, x equals 1, x equals 3. So now I found the zeros of this relatively long polynomial equation without too much hassle. Does it always work on the first number you pick? No, but generally it's going to work pretty quickly. So let's say that you say, Mr. Clark, man, I really hate factoring. Even though we did it forever, I don't want to do it. Factoring is the bane of my existence. Okay, there's another way. We're still going to use synthetic division, though. And I'm going to call this kind of the guess and check method, even though this is a little guessy and checky. But this is more guess and check. So what we're going to do, get some space. We're going to do the same thing. And I'll make my list again. It was 6 over 1, so we had 1, 2, 3, and 6. I just like to have it there so I don't forget. What I'm going to do is I'm going to try different numbers until I get a 0. According to our theorem, right, I should have, what was it, 1 positive root, or 2 positive roots and 1 negative root? We did that way back up here. So I know when to stop working. This problem, so I've probably got 2 positives. I definitely have 1 negative. That's how I'm going to know when I'm done working. All right. So I'm going to set up my problem for synthetic division. 1, negative 2, negative 5, 6. All right. Fix that up so maybe I can draw a straight line. And I'm going to start with a 1, which we already know works, but I'm going to do it just for good measure, like we didn't know. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Negative 1 times negative 1 is negative 1. We get a negative 6, and 0. So this does work. Now, what does that tell me? I know I've either got 0 or 2 positive roots, right? So since I found 1, that means there's going to be another one somewhere in the positive numbers. So what I'm going to do is go through the positive numbers now until I find the second positive root. So the second positive number is going to be 2. And I've got 1, negative 2, negative 5, 6. 2 times 1 is 2. 2 minus, or negative 2 plus 2 is 0. 2 times 0 is 0. Negative 5. 2 times negative 5 is negative 10. And 6 minus 10, that is not one of our solutions. Next. The next positive possibility is 3. 1, negative 2, negative 5, 6. Please be relatively straight. That's pretty close. 3 times 1 is 3. Negative 2 plus 3 is 1. 3 times 1 is 3. Negative 5 plus 3 is negative 2. 3 times negative 2 is negative 6. Hey, those add up to 0. There is our other positive root. I do not need to check 6 because I know the maximum is 2 positive roots. Now I can check the negative roots. How many negative roots should I have? According to our theorem, we should have 1 negative root. So as soon as I find it, we're done. I'm going to start off with negative 1. Start at the beginning. 1, negative 2, negative 5, 6. Negative 1 times 1's negative 1. Negative 2 plus 1's negative 3. Negative 1 times negative 3 is positive 3. Negative 5 plus 3 will be negative 2. Will be negative 1 times negative 2 is positive 2. And we get 8. That is not a solution. The next one will be negative 2. 1, negative 2, negative 5, 6. I think you can see why I'm using synthetic division instead of solving it algebraically every time. Negative 2 times 1 is negative 2. And we get a negative 4. Negative 2 times negative 4 is negative 8. I'm sorry, positive 8. Integer rules. Negative 5 plus 8 will give us 3. Negative 2 times 3, negative 6. Yay! So there is our single negative root. So that means going through all this malarkey that my zeros are x equals negative 2, 1, and 3. Now, that was the same problem in 2 different ways. I want you to remember this. We already did this problem up here, and look how much shorter that method is. This is the method that I prefer because I don't like doing a lot of extra work. But either method is fine. And synthetic division will make your life much easier when you're trying to evaluate these polynomials to figure out what your solutions are.